Good afternoon for those on the East Coast and good morning for everyone else. I hope you enjoyed watching our Capture 3D team video while waiting for us to get started. Alright, welcome everyone to the fourth episode of our webinar series. This is Sonia Jones, an event manager at Capture 3D. First off, we would like to thank you so much for taking the time out of your day and joining us on our 1-hour webinar. Today, we'll discuss the consumer goods, top 5 features for digital engineering, and we'll have a live Q&A session at the end of the presentation. We try to make our webinars as informative as possible for those that are new to our solution as well as for our current users. We have a lot of exciting things to cover today, and there are 5 features that our experts believe are very useful in the consumer goods manufacturing industry, and we are going to show you how you can utilize them. So the 3 out of the 5 features that our experts picked are actually available in our free GomInspect Suite software. So if you don't have the software already, you can download it from our website and you'll be able to try the features yourselves. One more thing that I wanted to note is that we are offering a free virtual GomInspect software training in 2 weeks, and it's open for everyone to attend. So please make sure to download your free software for inspection and reporting and attend our 3-day training. As I mentioned earlier, today's webinar is our 4th topic in our webinar series, and here's basically a list of the other applications that we'll be covering in the following months. So we normally host a webinar once a month or so, and if any of these webinars interests you, please make sure to check out our social media or website where we'll be posting updates on them. We also have recordings of the past webinars available on our YouTube channel, so you can check them out as well. Just a quick note, if you have any questions for our speakers during the presentation, please leave them in the chat below and we'll address them during our Q&A at the end. Please also make sure to direct your questions to all participants so everyone, including the host and speakers, can see your comments or questions. And when all attendees, not participants, attendees are selected, it's directed to the audience only, so we won't be able to see your chat. Without further ado, I'd like to introduce your panels for today's webinar. I'm Sonia, your host for the event, and I've been with the company for 4 years now, and I'm based out of our California office. As for the speakers, we have Jordan Myers, there he is, who is our sales engineer, and he's been with the Capture 3D for 1.5 years. We also have David Helton, who's our application engineer, and has been with us for 4 years now. Both of our speakers are based out of our Michigan office, which is our largest facility. All right, so thanks again for joining us, and we're really excited to have all of you with us today. With that, we're going to move on to our presentation portion of the webinar. Jordan, the floor is yours.
Thank you, Sonia, and thank you everyone for attending today's webinar. I'm excited to get started. For this webinar, we'll be exploring the current trends of the consumer goods industry in the United States, why 3D metrology is contributing significantly to the modernization of the industry. Then we'll be diving into the top 5 digital engineering features that David and I have picked out that we feel that have been impacting the industry in big ways, from product development, tool making, quality control, to production. If you have any questions during this webinar, please feel free to send them through the chat. We'll be having a live Q&A session immediately following the event. So we have a lot of cool things to discuss today, but to start, I want to go over who we are and what we do. Capture 3D is solely focused on GOM technology and software, which allows us to provide the highest quality of support and expertise to our customers. Our headquarters is in Southern California, and we have 4 supporting offices throughout the rest of the United States. The Michigan office is the one that David and I work out of every day. Our Capture 3D family is growing at an incredible rate, and we have over 100 team members. 65% of those team members are comprised of engineers. We have over 2,800 systems installed here in the United States and over 17,000 systems installed worldwide. This is just a sample of some of the companies within the consumer goods industry that are using our technology. Usually, our customers are about 35% aerospace and power generation, 35% automotive, and the remaining broken up between medical and consumer goods. But in the past years, we have seen a tremendous growth in the consumer goods sector, from appliances to high-tech electronics, and even video game development. The consumer goods sector has three main types, and we'll be focusing on the durable and non-durable goods. These are products that you and I use on a daily basis. It contains items that we probably take for granted, but each product has an engineering design and intent behind it. The graph here at the bottom depicts the total production of consumer goods manufacturing in the United States from 1960 to 2018. The gray areas represent where our economy fell into a recession. Following 2009, we had some offshoring and reshoring initiatives that since then have caused the market to be growing. Now to take a deeper look into the consumer goods here in the United States. The United States is a global leader in the consumer goods industry. The industry, especially with the high-tech electronics sector, moves at a rapid pace to meet the consumer demands. Products are being designed to be sleek, durable, and minimalistic, while engineered with multi-functionalities. One example is the evolution of mobile phones and smart devices. One of the contributing factors to the success has been our highly skilled workforce, which has helped us build the market to an estimated $635 billion. It's estimated that we spend approximately 30% of our personal earnings purchasing consumer goods. So understanding that the consumer goods is a key market within the United States, let's cover the needs of the industry. The needs of the industry can be broken down into 5 main points, and they are the demand for faster time-to-market strategies, increased product functionality, quality, and design, reduced processing and costs, which take additional time, and the need for comprehensive data, and last, better communication between teams and departments. So to meet those needs, one of the biggest trends is the adoption of 3D scanning technology. By implementing 3D metrology, companies are digitally transforming engineering processes to develop new strategies to streamline product development, manufacturing, and production processes. Some of these initiatives include Internet of Things, Digital Twin, and Quality 4.0. And the reason 3D scanning technology has played such a huge role is because of the accurate full field data able to be captured. In the recent years, we've seen a tremendous increase in the adoption of our technology, not only with startup tech companies, but with iconic consumer goods manufacturers that have been producing products for more than a century. One example is GE Appliances. This slide shows how they are using our ATOS technology within part qualification, root cause analysis, equipment verification, reverse engineering, tool verification, CAE or simulation, VR analysis, and product quality control. This has been a game changer for their team, and they've modernized their processes not only in the United States but throughout their facilities around the world. The consumer goods manufacturing process has many different stages, from the design and CAD creation to the FAI and assembly. Sometimes these stages are spread across different companies, making the product life cycle even more difficult to see. But when you can create a digital version of that part, it becomes a lot simpler. With all these different stages and companies, one would say that a product that could be used at each stage and in each company would be a real all-in-one product. Well, 3D scan data, and by extension 3D metrology, is that all-in-one product. When discussing the life cycle of a product, you can see that it goes through many different stages and departments to create from what becomes just a digital idea to an actual physical part. Now that we have an understanding of the 3D metrology inside the consumer goods manufacturing process, I would like to hand things over to David here to go over the ATOS process and how the actual system works.
Thank you, Jordan, and hi everyone. David here, and I'm going to explain in short the ATOS process. It's a real easy 3-step process. Step 1, we got to start with a measurement. So this is when we gather data on our part, and in fact our fringe pattern gathers millions of data points across our part that we will use in our second step, which is for evaluation. Step 2 in evaluation, this is when we can see the cleanness of our mesh and how it's going to compare back to our CAD model. So this is when we do our alignments and all of our inspections really. You can do anything from color mapping all the way over to features inspections, GD&T, section cuts, all sorts of inspections you can do that you're all familiar with already inside the ATOS software. Finally, we can wrap it up with step 3, our inspection report table. You can create an easy to read report via 3D images, or you can go the more classic route from like a CMM, which would be a tabular data set. Now, Jordan, are you going to go more into the full field data acquisition?
Sure thing, David. Full field data is a huge contributor to the benefits over other tactile measurement systems. When we say full field data, what we mean is you get the whole part, not just the tactile contact spots like you do on a CMM. This is greatly beneficial for the end user because you can go back to the data set without rechecking the part and do a remeasurement of that part. With that, you can also add to the existing or create a new measurement report, which then includes the original areas of interest along with the new ones that were added to the visual report. A little hidden gem inside ATOS is the ability to create 3D PDF reports within the software for a nice, innovative way to present our data set. With the information we have covered so far, we would like to go in depth into the real-world application that we have been given the privilege to share with you all. The real-world application we are looking at will be focusing on one of the most popular questions we get in 3D metrology. How does this compare to using a CMM? CMMs have been a metrology staple for many years, but with the world evolving around us to a more traceability and less waste in time and materials, we have seen the CMMs being replaced by 3D metrology. Jabil is a leader in manufacturing a large variety of electronics. With 60 sites worldwide and over 140,000 employees at the time of this presentation, they had 12 ATOS 3D scanners. Jabil conducted a correlation study between one of the leading CMM brands and an ATOS 3 triple scan with 170 measurement volume. Using a VDI acceptance test, both technologies were able to achieve below 5 microns. All measuring volumes in all ATOS systems come with a VDI acceptance test. David, can you give us a quick explanation of what a VDI acceptance test is?
Certainly, Jordan. A VDI is a standardized acceptance test used for optical systems. It's very similar to the B89 routine like on a CMM. We measure a defined pair of spheres based on their probing error, which is just a best fit result with sigma and range. We also measure the probing size, which is nominal to actual size difference. The sphere length the sphere length error, which is a distance between the sphere's polar points, and the sphere spacing, which is the center point to center point between the two spheres. This is all done automatically via the VDI script and just click of a button. Now, Jordan, is there anything else you'd like to touch on pertaining this case study?
Yes, thank you, David. And the next 2 slides we'll go and look into the actual 2 studies done by Jabil. The first study was to analyze their mold inspection time. Jabil was an early adopter of the ATOS technology, using ATOS in conjunction with their CMM. That process took about 3.5 hours to scan and inspect their mold. By eliminating their CMM and using ATOS exclusively for scanning and inspection, they were able to save about 2 hours of inspection time just for the one mold. The second study was analyzing the first article inspection time. Often, the most cumbersome and time-consuming part of the CMM process is programming the probe to touch in the correct areas of the surface for the inspection. With ATOS, there is no probing, but we are capturing full field data instead. There is a little setup in comparison to the CMM, Both were done by the manual inspection process. For the ATOS, this means by moving the system around on a camera stand to complete the inspection. And as you can see from the table and graph below, using the ATOS system, we had a 400% increase in the inspection time. With JBuild, the overall process optimization was key for them, along with the rapid data collection for their dimensional analysis. When speaking with our customers, these were the main challenges that were overcome by using our technology. Immediately resolving quality issues, reducing of processes, because now we have more data to make a clear, sound decision, freeing up more time to critically think, expand capacity, improving part quality, avoiding potential future issues that could have cost us money, which were found earlier. With all of these come a faster time to market. Speaking of the benefits, another thing that I would like to note is that optical 3D scanners are portable, scalable, and come in a variety of configurations. We have many different configurations of our ATOS system, from the manual to the fully automated. The top row displayed shows that our manual systems and semi-automated, followed by the middle and bottom rows showing some of our fully automated configurations. Let's start with laying out the top 5 features for digital engineering. Number 1, 3D visualization and reverse engineering. Number 2, tool verification and dimensional surface defect mapping. Number 3, digital assembly for virtually bringing together data. 4, live tracking and back projection. And 5, trend analysis for intuitive monitoring. Let's kick things off with number 1, 3D visualization and reverse engineering. We will be discussing a few different features within this section. Let's start with something we like to call 2D image mapping. Oftentimes you'd like to overlay color onto your STL scan data to have a digital representation. David, can you showcase how this works?
Sure thing, Jordan. I'll go ahead and showcase a little bit of the 2D color mapping. Everyone, here we have a data set of the leprechaun, and I want to get a color mesh here. So I need a reference image. I'm going to go ahead and use an image. Now you can use an image from your digital camera, your cell phone, whichever, and go and import this image into the project. But first things first, let's go ahead and select our image like I have here. And I need to select some reference points. So I'm going to go ahead and select on the side of the cheek here. Again over here. I'm going to select on the bottom of the belt down here and on the shoe. And once I finish on my shoe, I'm going to go ahead and hit one more point, looking for 5 up top on the thumbnail over here. And you can see my image go ahead and wrap. And you can see a mesh slightly behind it. I want to cut this color onto my mesh so I can go to my function inside of the software, go ahead and select the mesh I'd like right here, and you'll see now on my mesh I have a full color representation of my part. It's pretty neat. This is used for really if you want to check like contours quickly, contrast between edges and stuff on toys or molds or dies, whatever it may be. And you won't need very many things either. All you're going to need is a 2D image, the 3D mesh of the part you're trying to throw the color onto, and our GOM software. Jordan, could you please explain augmented reality to the audience?
The next feature I want to discuss is available even in the free GOM Inspect Suite software. This feature is augmented reality. Basically, as the name suggests, you can use a Windows tablet that has a camera and augment the real-time camera feed with a color map inspection against the actual part. This comes in handy when you want to discuss some of the dimensional elements directly on the part. As you move around, the AR also follows to show you the areas that are in and or out of tolerance. Another way to use 3D scan data is for virtual reality. 3D scan data is like a digital blueprint. The dense number of actual 3D coordinate points opens up even more applications in which you can use the data. GE Appliances utilizes their ATOS scan data into their virtual reality headsets to simulate their product into a fabricated world. Not only can you interact with their product through this simulation, but you can immediately change the environment to see how the product looks against various settings.
Thank you, Jordan, for the explanation. Now, how can we apply this into Atos to easily visualize our data set for reverse engineering? Let's take a look real quick here with this Adidas golf shoe, and I also have my daughter's Converse for reverse engineering. So to visualize our data a little bit better, we can see here the definition from our Atos 5 scanner. The definition on our leather is very defined, the mesh structure of the shoe, the ridges on the laces, but what does that mean and how can I see all these data points? So to do that, I can easily visualize these 3.2 million data points by turning on my mesh structure. So here that we see is each polygon is 3 data points. As you see, the triangle has 3 points to it. That is each a data point. So if you take that to a CMM, this is about 3.2 million touches from a CMM that our Atos scanner captured within minutes. Try to do that on a CMM, that will take a very long while. Now, the nice thing and my favorite little hidden gem inside of Atos is the ability to zoom in to the detail and look down through things like through holes, through cavities, and so on. A lot of the softwares around, you zoom in and you want to look at the underside of this, you get blocked like so. I have the ability now to change my perspective. I can visualize this a lot better and go into my shoe if I wanted to, as you see here. And I can look down on the inside of my shoe. I can go through cavities, I can go through holes, really anything. And you can see I can check the inside of the shoe out. Really see in there in nice, clean, crisp data and nice detail. Real easy to visualize, easy to turn. You can change the color of the mesh. If you don't like that color, you can change. You got a whole list of colors of the mesh you can change here. Now, what can we do for reverse engineering? Well, with reverse engineering, you need a clean data set, and that's where Atos really thrives, like you see here. Let me bring out my daughter's Converse here that we see. And I'm looking for a mold. I need to build a CAD model. I don't have any. Reverse engineering with Atos is a breeze. DesignX is built right on into it and it's easily exported out. So what we can do with Atos and reverse engineering is use our function called a golden mesh. As you can see on the bottom here, I have 3 meshes in here at the bottom of my daughter's shoe. And I'm going to take these and I'm going to average them out with our function golden mesh, as you see here. And what this does is I can come in here and select what mesh to compare against, but I can say, hey, find the best mesh out of my run, as you see on the bottom, or create an average mesh out of my run. What I did, I went ahead and created an average mesh, which I'll bring out, and that is this mesh right here. This mesh here, I can take it right to DesignX very, very easily. And to do that, you just right click on your mesh and say export to DesignX. It's built right into the software. Taking that over to DesignX with the full field data, you can create a CAD model within minutes. DesignX is really powerful too. That even has the auto surface feature where I can literally just bring it into DesignX, hit a button, it will surface everything and create a model. That's really nice for Atos and DesignX because we get that real crisp, clean, watertight data set. Now from here, I get my model back into Atos. And now what I can do with this, reverse engineering possibilities are endless. I can take this model, I can thin it out, I can take it to a 3D printer for printing, I can take it to a CNC machine for milling, I can do inspections to it. Just for example, I'm gonna compare all 3 of my meshes here back to that average model. And as you can see, I cycle through and you can see the color map change. I can place my labels down just to give you a visualization here and you'll see the label change. Everything is being compared back right now to that golden mesh. Again, it's an average mesh. Jordan, can you go ahead and get on to our next topic, dimensional analysis, while I get our next project ready?
Yes, David. Our next topic, number 2, is dimensional analysis. With Jaba, we discussed how they use Atos 3D scan data for their FAI and the inspection of their toolings. I just wanted to quickly touch on the other use for 3D scan data for mold flow or magma situations, multi-cavity inspections, form, fit, and function, shrinkage and warpage, and we'll go into detail with surface defect analysis. The images on the right were mold flow modifications of Oshler using ATOS 3D scan data, which gave them intelligent insight to properly make changes. They are another company that graduated from using a CMM to an ATOS. Now to move on to our next topic, surface defect. Surface defects can be a major contributor to good parts ending up in the waste bin. From flash and form markings from the injection molding process, to surface deformations of metal support structural components. These are all surface defects that contribute to the losses of production from plastic injection to metal castings. Surface defects are imperfections that are experienced by many different production processes, no matter the material used. Some of these defects are hard to measure using standard touch-based inspections. After working with some industrial leaders in the plastic injection molding, we have been able to calculate and reduce the occurrences of these defects. With the use of the ATOS, we can see the entire surface using the full field data analysis, which gives us a more complete picture of what the part is experiencing after the injection molding process. With this information, we are able to see the overall surface changes in a part that a normal touch-based inspection process would miss because of the lack of the full field availability. David, could you explain how we can quantify these surface defects by using an ATOS system?
Sure, Jordan. Let me help you explain this a little more by visually showing the audience. So here we see on our screen is our multimedia part. And the key thing about surface defecting mapping is you might not always be able to see the defects with the naked eye. And that's when the ATOS algorithms come into play. So we're interested in the defect that we can vaguely see on this plane surface there and over here on the back side on this curved area over here to see how the support is playing a role on the exterior surface. So for here, I want to create a plane-based selection. So I'm going to come up to my selections in 3D and go over to plane-based. I'm going to go ahead and select this area, and you can kind of see the defect highlight a little more, but we're not done. Now I can construct my defect map. Now I went ahead and already did this, so I'm going to go ahead and show you the final result right here so we don't have to wait for it to calculate. Here is our final result. You can see it visualized now with color. Very easy to read. Now I'm going to go ahead and edit this, and I can change the direction. Right now I'm checking this in the X direction. I can go ahead and say, hey, check it in the Z as well. But let's go back to the X. Now the number of directions, this is really neat. You can do one direction, which is just that X direction, or we can say two, and it goes orthogonal to the surface. That's my go-to. Now a little tip here, if you want to check for just bulges, you can. If you want to check for just depressions, you can, or both. Here we went ahead and went with both. Now I'm going to throw down my deviation labels. The defect we weren't able to see very well with our naked eye, we can clearly see now and put a numeric value to it with our surface defect mapping, which is really neat. Now that I mentioned on a plane surface, let's look at the curve. So here's our curved area, and I want to check the strain on the support behind that little through hole there. Since our software is parametric, I can go ahead and select more of this area and dive into the direction. Now, as you see here, I changed my direction to go perpendicular to the surface of my curve, and you can see the strain now on our plastic surface there from the support behind it. And I can quantify that by throwing down more labels, deviation labels, and I can also make my selection larger like I was saying. So here it is above our CAD model, so it is protruding out just a little bit. Now that's something you would not be able to see with the naked eye. You would only really be able to see when you dive down with the ATOS software and our ATOS hardware paired with it. Jordan, is there anything else that you want to go over? I believe next might be digital assembly.
Correct, David. Our next topic is number 3, digital assembly. Now, most of our consumer goods are not single parts. They are multiple parts assembled together, and the more complex our world becomes, the more our goods we use every day will do the same. We are all looking for that all-in-one product, similar to the way some of our customers see the ATOS system as the all-in-one inspection system. Even something as simple as this cart body has multiple components that must be assembled properly to operate. If they are not assembled properly, you can see many different kinds of issues that can arise with the final product. Another example is the Xbox controller. David, could you show us the scan data and give us some more in-depth presentation on digital assembly using the controller?
Absolutely, Jordan. I have the Xbox remote open right now here. Okay, everybody, this is a familiar item in a lot of households if you're a Microsoft fan. And as we're all familiar, the Xbox remote is comprised of 11 buttons, 2 joysticks, and 1 D-pad, and many more internals on the inside. And they all kind of need to work together in unison to give you a nice end result, a nice finished product. So how can these really be inspected as a single state and an assembled state? And that's when the GOM ATOS digital assembly come into play. So let's take a little bit deeper look here. Like I said, on our screen we have our actual mesh data of our Xbox remote. And I'm going to go ahead and remove the front plate, our joysticks, our buttons, and we can kind of see how what's inside and how everything is fitting in our back plate here. And what I'm really interested in is how our board fits to this back plate and our fastening areas. And to do this, I need to create a surface comparison here to my back plate on my board. So I'm going to go ahead and drag that out, and we get this nice heat map here. The red areas are above CAD and the green is right on where we need to be. So it looks like in my fastening areas I'm putting down 3 deviation labels, and they seem to be right where I kind of want them. A little high, but we're all within tolerance. So that's a good sign so far. So as you can see, I'm inspecting this board as it is in my assembled state, like you saw at the very beginning. The next thing I want to look at is my D-pad here. The gap around the D-pad to the front housing is very, very crucial. We don't want the gap to be too small on one side and larger on the other. So here I did a gap check, and we can see now that we're uniform all the way around. The travel between the left to the right, the top to the bottom, and the corners, diagonally I should say, not corners, all are within uniform. They all will travel very well. Now another big thing is our joystick distances. The joysticks need to be pretty spot on. Our average human thumb is 2.74 inches long. We need to make sure the distance between our 2 joysticks is where they need to be. So I went ahead and constructed 2 cylinders and did a distance check as I was speaking here. I'm going to put in my tolerance of 0.5, and according to my print we should be at 61.2. Let's see what we checked at. I'm going to go ahead and turn on my results. We're at 61.7, so we're a little above where we need to be. Now this could be either the joystick has been rather used quite a bit and they're getting a little loose, or it is just a manufacturing issue, and we can dive in a little deeper and figure out how that was done. Now we saw how our Xbox was kind of built in reverse. You can do that the other way around. We can start from the beginning, or the end rather, and build up to the finished product, and you can see how the pieces fit that way as well. So not only do you get a numeric value when you do a digital assembly, but you can also get a visual value as well. You can do a visual check on the part. Jordan, is there anything else that we need to cover?
Yes, David. And our next topic is number 4, live tracking and back projection. I know live tracking is one of your favorites. Would you like to explain this one?
Thank you, Jordan. And this is one of my favorite topics to talk about. I'm really excited to show everybody some of these videos of live tracking and back projection. Now, let's get started. So with live tracking here, I'm going to throw out this video. Here we go. We can see a muffler not in position indicated by the color map. We can live track this muffler and fasten it down to position. So you see in the video he moves it over into the correct slot, and now he's orientating the muffler to get that all green position, and he'll fasten it down. A good way that customers use this is for kind of what you see on the video now. Another way is you can locate and make sure the fastenings are in the correct spots. You can live track that. For your car seats, you can live track the mounting brackets, or you can even live track how does my part fit inside of my mold, which is neat, and I'm actually going to show you that here right now. Now here in this video we have our sand core mold and our sand core. And how does our sand core fit inside of the mold? We're going to use the same kind of methodology that we used for the muffler video previously. will indicate good positioning when our sand core turns that nice green color, and we can fasten it down. But right now there's no fastening. We're just seeing how does this fit inside of our mold, and we can see we're pretty nominal but heavy a little bit in the front. Now, how is all this being tracked? It's using reference point markers, and you actually have to set up a component, which is real easy to do in the software. And when those reference markers are near that component, you'll see a color map appear on your part. And you can move that in that given area, and you'll get a live feedback of if you're in position, or even numeric values you can use as well, not just a color map. Now, moving this on to back projection, we can actually take this and back project onto our part, which I believe is our next little segment. Am I right, Jordan?
That's correct, David. The next topic is back projection. In the world of consumer goods, we experience a lot of situations where seeing data or reports does not always translate to understanding the issue. In the consumer goods industry, we must be constantly looking at our manufacturing and trying to understand how our tools are affected by the production of our parts. For issues like this, we have back projection. Back projection is where we can take the data we see on the screen and project it back onto the part. This tool is one that can benefit our manufacturing of consumer goods. This is great for understanding the material wear of dies during the manufacturing of the products, as well as seeing the corresponding material buildup on those products. David, using our injection molded part and the mold itself, could you please show us how we could use this back projection?
I sure can, Jordan. So everyone, piggybacking from earlier with our multimedia part, let's see now how we can project these imperfections back down onto our mold to see how our part is fitting in the mold, or if our mold even has some slight issues. So let's go ahead and take a look. So the first thing I'm going to do is project this color map down onto my part. So I turn on my ISO lines and I go ahead and go to my tracking, and I'm going to project it right on down. And you can see it in our live view, the projection of our ISO lines. But now let's take a look on a real part. So here you can see it's on our real part, and you can use this for marking. This is when you can come over and mark on your mold or even on your physical part any imperfection of the color map. Now you don't need to do just color maps, you can do geometries as well. So here I'm going to project our surface points. These surface points are, I kind of just arbitrarily made them. They're not any of importance really, but a great feature to use this on would be like fastening holes, or marking a location of a critical feature, or if you need to implement a feature, like let's say a point right here or a punch mark, you can go ahead and put it there while it's being projected onto the part. You see the spiral there, and this is our true mold here. Now you don't necessarily need to do just features like so. You can do a point, you can do a circle. So here we have a circle 1, and I can project this down onto the mold as well. Same way as I was doing before. You can see it projecting now onto the mold from my part. And now let me show you on the actual mold itself, the circle being projected. Very easy, very clear to read. You'll see it spin and then lock into place. Now this is all done by one person, no two people needed, and you can just do it all back projection with one. A curve can also be done. So I'm going to show you a curve now. I made a curve around my part here, and I'm going to project this down onto my mold to see how my curve is fitting inside the mold. Again, here it is on our live view. Now let me show you what it looks like on our actual part here. And let's project it down. Here we go. And there's our curve that we made on our part on our actual mold. And you can do any sort of deviations, again, any sort of markings of the deviations all throughout your back projection process.
Thank you, David. That data was spot on. Now let's begin number 5, trend analysis. Trend analysis allows us to compare multiple parts back to a single CAD model in a project for the purpose of batch scanning or production assistance. Trend analysis also allows us to inspect via part-to-part inspection for the purpose of comparing multiple scans of each other when a CAD is not available or useful for our desired inspection. Using trend analysis, we can even represent trends across parts that were made with different tools. We can display these trends in a single project using GD&T, color maps, or geometric elements. We could even use a single label if that was desired. David, could you now show us how the trend analysis works using our drill housing?
Absolutely, Jordan. I have it ready to go right now. Everyone, as you see on my screen here, is our Dewalt drill housing, and we're inside of a trend project, which is indicated on our bottom here, the timeline that has 11 of our meshes inside our trend. Now, I'm interested in seeing how each one of these meshes compare back to my CAD model. So let's go ahead and drag a mesh out, and you can see now we have a high detailed clean mesh, and as I cycle through, you can see it subtly changed during our part run. So we're interested in how does this compare back to our CAD model. So to do that, we can just do a color map here, a surface comparison, and put down some deviation labels to quantify this. So as I place these down inside my trend, I can now cycle through each one of my stages and see of my areas of concern. How is it deviating from the CAD model? Now this doesn't need to be with just surface comparisons. You can actually do this with geometries as well. So for example, this circle here, I can cycle through each one of my stages and see the diameter change of this circle. But what if I wanted it to go from, let's say, part 2 being compared against part 3, part 4, part 5, and so on? You can easily do that inside of a trend project. Let me show you how. So we're going to manage our stages and make this one reference. So now you'll see now that this went to 0 deviation, or nominal is really this one now. So as we cycle through, you can see the diameter change. We're doing a part-to-part comparison. Now, this is all in a separate label here. We have to cycle through. We can make it real easy to read too if we do a trend label. It's as easy as just changing the visualization. And now you can see as I cycle through each one of my my meshes down here, my parts, we're indicated with a vertical line where we're at. And we get a whole min-max with our PPK and PP values all in one label, very easy to read. And now if I want this to go back to a CAD model and not so much back to part 2, it's as easy as undoing that reference and it will go right back to the CAD model automatically. As you see, our map changed, our values changed, and I can cycle through. That wraps up the drill housing, Jordan, and I believe that was our last topic of discussion today.
Thank you, David. That was all 5 features we wanted to cover for today's webinar. But as you can see from this list here, there are many other features that could be useful for your application that we just did not have time for today. The professional version of GOM inspection software contains a list of very powerful tools at your disposal, allowing complete dimensional evaluation of even the most complex parts. GOM is focused on staying ahead of the competition by continuously innovating new capabilities while also enhancing existing functionalities year after year. If you are interested in learning the basics of the GOM Inspect software, you can download the online version of GOM Inspect from the website listed here. This is a very powerful software offered by GOM for free. It can be used as a viewing tool for sharing reports and projects within your organization at no cost. It can even be used to upload data from other measurement technologies such as laser scanners, CT, or other structured light systems. And as Sonia mentioned, we'll be offering a complimentary virtual training using the GOM Inspect software on November 10th through the 12th. Make sure to visit capture3d.com to register while seats are still available. David, do you have any final comments before we move on to the summary for today?
I do, Jordan, thank you. And thank you again for everyone attending today's webinar. Should any of you be interested in receiving a sample inspection report that is highlighting some of the features that we showcased today, just drop us an email at info@capture3d.com and I'll gladly send you one over. I hope you have enjoyed our technical review that showcased some of the software features and not all. Our Q&A session is due to start here very momentarily for any questions that you have for Jordan and I. Jordan, that's all I have for everyone. Is there anything else that you would like to add?
No, David, I have nothing to add, but I would like to sum up today's webinar. We started off with reviewing the consumer goods industry and how it's rapidly evolving every day. And then we discussed how the 3D metrology is helping that revolution of the manufacturing. And then we finally got to the bulk of the webinar about our top 5 digital engineering topics. 3D visualization and reverse engineering, where we went over this by using our Adidas golf shoe and David's daughter's Converse. Then going into tool verification and the dimensional surface defect mapping, where we used our multimedia part. Digital assembly, where we virtually bringing our data together using our Xbox controller and the multiple components inside it, followed up by live tracking and backwards projection, where we again revisited our multimedia part and the mold this time. And we finally got to our trend analysis, where we used our Dewalt drill housing to see how we could use that inside our ATOS software.